It was 1929 when Edwin Hubble made the announcement that would rewrite everything. Galaxies are moving away from us, not some galaxies, all of them. The farther away a galaxy is, the faster it recedes. Space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. This was revolutionary. For all of human history, the cosmos was assumed to be static, eternal, unchanging. Even Einstein had introduced a cosmological constant into his equations specifically to keep the universe from collapsing or expanding. When Hubble showed expansion was real, Einstein reportedly called it his greatest blunder. But here's what's strange. After the initial shock wore off, everyone just accepted it. Expansion became the foundation of modern cosmology. The Big Bang Theory emerged naturally from it. If the universe is expanding now, it must have been smaller in the past. Wind the clock back far enough, and everything converges to a point, the hot, dense beginning. Cosmic microwave. Background radiation confirmed it. Element abundances matched predictions. Expansion became settled science. Textbook material, the kind of thing undergraduate physics students learn in their first cosmology class without questioning. Except we should be questioning it. Not whether expansion is real, the evidence is overwhelming, but what expansion actually means. Because when you dig into the details, when you really think about what it means for space itself to expand, the concept becomes deeply weird. We talk about it casually now. Space is stretching. Galaxies are being carried apart. The fabric of the cosmos is growing. These phrases roll off the tongue easily. But what do they actually mean? What is space that it can stretch? What does it mean for something that isn't made of matter or energy to grow larger? Think about it this way. When you stretch a rubber band, you're pulling molecules apart. The rubber band is made of atoms held together by electromagnetic forces. Stretching means increasing the distance between those atoms against the forces binding them. But space isn't made of anything. It's not composed of particles or fields in the conventional sense. It's the arena where particles and fields exist. So what are you stretching when space expands? What's getting larger? The mathematics is clear. Einstein's general relativity allows for expanding solutions to the field equations. The Friedmann equations describe how the scale factor of the universe changes with time. These equations work beautifully. They predict cosmic expansion. They explain observations, but the mathematics doesn't tell you what expansion physically is. It tells you that the distance between non-interacting objects increases over time. It tells you how that distance changes as a function of matter and energy density, but it doesn't explain what's actually happening. What mechanism causes the increase? What is the thing that's expanding? You might think this is just semantics, philosophical navel-gazing. The math works, the predictions match observations. What more do you want? But this is not just philosophy. This is about understanding what's really happening in nature. And when you look closely at cosmic expansion, truly think about what it implies, you find something unsettling. The standard story has holes, not in the observations, those are solid, but in our interpretation of what those observations mean. Here's the first hint, something is off. Expansion is supposed to be uniform. The Hubble constant describes the expansion rate. Same rate everywhere. Every cubic meter of space expands at the same rate as every other cubic meter. This is the cosmological principle in action. The universe is homogeneous and isotropic on large scales. Expansion respects this symmetry. It's the same everywhere, pointing in all directions equally, except it's not. We live in a galaxy. Galaxies are held together by gravity. They don't expand. The Milky Way is not getting larger. The distance between Earth and the Sun is not increasing. Atoms aren't expanding. Your body isn't expanding. Objects bound by forces don't participate in cosmic expansion. Only space between gravitationally unbound objects expands. This seems reasonable at first. Of course, bound systems don't expand. Gravity is stronger than expansion on small scales. The expansion only manifests in the vast spaces between galaxy clusters where gravity is weak. But this creates a conceptual problem. If expansion is a property of space itself, why does it care whether objects are gravitationally bound? Space exists everywhere. Inside atoms, inside your body, inside galaxies. If space is expanding everywhere uniformly, why doesn't everything expand proportionally? The standard answer is that expansion creates a tendency for distances to increase. But local forces can overcome this tendency. Gravity holds galaxies together, despite expansion trying to pull them apart. Electromagnetic forces hold atoms together. The expansion is there, but it's overwhelmed by stronger forces on small scales. This answer works mathematically. The equations support it. But physically, it's odd. Expansion is supposed to be space growing. If space inside a galaxy is growing, what compensates? Are galaxies being compressed by expansion while gravity stretches them back? Or is the space inside galaxies somehow different from the space between them? Nobody really knows, and most cosmologists don't think about it much because the math works and the predictions match observations. But some researchers have started asking uncomfortable questions. What if expansion isn't what we think it is? What if the universe isn't actually expanding in the sense of space stretching? What if something else is happening that looks like expansion but is fundamentally different? What if we've been interpreting observations through a framework that's approximately right but misses something crucial about what's really going on? This is not fringe science. These questions are being asked by serious researchers in peer-reviewed journals, because the more precisely we measure expansion, the more anomalies appear. The Hubble constant gives different values depending on how you measure it. A tension that's persisted for over a decade and only gotten worse with better data. Expansion appears to accelerate, driven by mysterious dark energy that we cannot identify or explain. Some observations suggest expansion might not be uniform, that different regions of space expand at different rates. The simple picture of uniform cosmic expansion is showing cracks. The universe is expanding. This is not in doubt, but that's not the mystery. The mystery is what expansion actually is. What causes it? What's really happening when we say space is stretching? Whether the framework we've used for nearly a century to interpret observations is complete, or whether something fundamental is missing. The mystery is whether we truly understand the phenomenon that underpins modern cosmology, or whether we've been measuring a real effect while completely misunderstanding its nature. Let's find out. Measure the distance to a nearby star. You can use parallax. Watch how the star's position shifts as Earth orbits the Sun. The shift depends on distance. Closer stars shift more. The geometry is straightforward. The distance you measure is what you expect distance to mean. The space between here and there, the path light travels, the number of meters separating 2 points. Simple, intuitive. Now measure the distance to a galaxy 1 billion light years away. Suddenly distance becomes complicated, ambiguous, dependent on what you mean by distance. The light you observe left that galaxy 1 billion years ago. The galaxy is not where you see it anymore. It's moved. Space has expanded during the light's journey. The galaxy is now farther away than it was when the light was emitted. So what is the distance? The distance when the light was emitted. The distance now. The distance averaged over the light's journey. Each definition gives a different number. None is obviously wrong. Each is useful in different contexts, but they're not the same. In an expanding universe, distance is not a single well-defined concept. Cosmologists use multiple distance measures. Luminosity distance relates to how bright an object appears. Proper distance is the distance you would measure if you could freeze the universe's expansion and stretch a tape measure across space. Co-moving distance factors out expansion, treating space as if it weren't expanding. Angular diameter distance relates to how large an object appears on the sky. These are not different estimates of the same thing. They are different concepts, each meaningful in its own way, giving different numerical values for the distance to the same object. This is our first hint that expansion is weirder than it seems. In a static universe, distance is unambiguous. The space between 2 points has a definite size. But in an expanding universe, even defining what distance means requires care. You have to specify what you mean. Distance when? Distance measured how? The fact that we need multiple definitions of distance suggests something subtle is happening that our intuitions don't naturally capture. Now think about velocity. A galaxy 1 billion light years away recedes at about 20,000 kilometers per second, according to Hubble's law. That's a velocity. Movement through space. Or is it? The galaxy is not moving through space in the usual sense. It's not zooming away like a rocket. Space itself is expanding between us and the galaxy. The galaxy is mostly at rest with respect to the local fabric of space. It's space that's growing, carrying the galaxy along with it. This is called the Hubble flow, galaxies participating in cosmic expansion without actually moving. But here's where it gets strange. The recession velocity of distant galaxies can exceed the speed of light. Galaxies far enough away recede faster than light. This seems to violate special relativity, which says nothing can move faster than light. But it doesn't, because the galaxies aren't moving through space faster than light. Space itself is expanding, and there's no speed limit on that. The distinction saves relativity. But it also makes clear that recession velocity is not velocity in the normal sense. It's the rate at which distance increases, which is different from motion through space. How different? Very different. Normal velocity adds. If you're on a train moving at 50 kilometers per hour and you walk forward at 5 kilometers per hour, your velocity relative to the ground is 55 kilometers per hour. But recession velocities don't add this way. Two galaxies each receding from us at half the speed of light are not receding from each other at the speed of light. The relative recession velocity depends on the geometry of expanding space in ways that defy simple addition. This is because recession velocity is not motion, it's the manifestation of space itself changing size. Except that explanation raises more questions than it answers. If galaxies aren't moving, if they're just being carried by expanding space, what does that mean for their kinetic energy? Moving objects have kinetic energy proportional to the square of their velocity. But galaxies in the Hubble flow have no kinetic energy associated with their recession. They're not moving in any frame that would give them energy. The expansion is creating distance between them without creating energy. This seems impossible. Where does the energy go if you artificially hold two galaxies at fixed proper distance against expansion? You'd need to do work. Energy would be required. Where does that energy come from? The answer involves the gravitational field. The expansion of space is intimately connected to how gravity works on cosmic scales. The energy balance is subtle and involves the gravitational potential energy of the universe as a whole. But this answer is unsatisfying. It shifts the mystery from kinetic energy to gravitational energy without really explaining what's physically happening. And it highlights that cosmic expansion is not just space growing. It's space growing in a way that's coupled to the gravitational field and the energy content of the universe in ways that are mathematically well-defined but physically murky. Distance and velocity are fundamental concepts. We think we understand them from everyday experience, but in an expanding universe, both become ambiguous. Distance depends on how you define it. Velocity is not really velocity in the traditional sense. Objects can recede faster than light without violating relativity because they're not actually moving. Explanations rely on space itself expanding, but what that means physically is unclear. We have excellent mathematical descriptions, the Friedmann equations, the metric tensor, the scale factor, all precise, but precision in mathematics doesn't guarantee clarity in physical understanding. We can calculate everything about expansion, predict observations, match data, yet still not truly understand what it is we're describing. This matters because it suggests our framework might be incomplete. Not wrong. The equations work too well to be fundamentally wrong. But possibly missing something, some deeper description, where distances and velocities have clearer physical meanings, where expansion emerges from more fundamental processes rather than being a basic feature of space itself, where what we call expansion is actually something else, something we haven't fully grasped because we've been satisfied with mathematical descriptions without demanding deeper physical insight. The universe is doing something. We call it expansion. But is that what's really happening? Or is expansion a convenient description of a phenomenon we don't yet fully understand? By the 1990s, cosmologists thought they had cosmic expansion figured out. The universe started with the Big Bang. It's been expanding ever since. Gravity pulls everything together, slowing the expansion over time. Eventually, if there's enough matter, expansion might stop and reverse, leading to a big crunch. If there's not enough matter, expansion continues forever, but gradually slows down. Either way, the universe should be decelerating. The expansion rate should be decreasing over time. This was not speculation. This was basic physics. Gravity attracts. Attraction slows expansion. Simple. Then in 1998, two teams of astronomers studying distant supernovae announced something impossible. Expansion is accelerating, not slowing down, speeding up. Distant supernovae were fainter than expected, meaning they were farther away than they should be if expansion were decelerating. Space was expanding faster now than it was billions of years ago. The teams checked exhaustively. They looked for errors. They considered alternative explanations. The conclusion remained: expansion is accelerating. This was shocking enough to earn the discovery leaders a Nobel Prize, but the shock was not just that acceleration was unexpected. It's that acceleration should be impossible. Gravity is attractive. It pulls things together. There's nothing in standard physics that pushes space apart, yet something is doing exactly that. Something is causing space to expand faster and faster, overcoming the gravitational pull of all the matter in the universe. Something is acting like anti-gravity, filling the universe with a force that drives cosmic acceleration. Cosmologists call this something dark energy. The name captures our profound ignorance. Dark because we can't see it. Energy because it has energy density that affects cosmic expansion. But what is it? Where does it come from? Why does it have the specific value it does? These questions remain unanswered. Dark energy is not just another component of the universe like atoms or dark matter. It's fundamentally different. It doesn't dilute as space expands. Normal matter becomes less dense as the universe grows because the same amount of matter spreads over larger volume. Dark energy doesn't work this way. Its density remains constant even as space expands. Every cubic meter of space has the same dark energy density regardless of expansion. This creates a runaway effect. As space expands, more volume means more total dark energy. More dark energy drives faster expansion. Faster expansion creates even more volume and even more dark energy. Acceleration keeps increasing forever. The universe's expansion will keep speeding up exponentially, eventually tearing everything apart. Galaxies beyond a certain distance are already receding faster than light and will never be observable again. In the far future, trillions of years from now, every galaxy will be alone, surrounded by darkness, unable to see any other galaxy because expansion has carried them all beyond cosmic horizons. This is the Big Rip scenario, the ultimate fate of an accelerating universe. Unless dark energy doesn't stay constant, what if it evolves? What if dark energy density changes over time? This would change everything about cosmic fate. If dark energy weakens eventually, acceleration might stop. Expansion could transition back to deceleration. The Big Rip could be avoided, or dark energy could strengthen, leading to even faster acceleration and an earlier Big Rip. Without understanding what dark energy is, we cannot predict its future behavior. We can only measure its current value and hope that tells us something about what it will do. But here's the deepest mystery. Dark energy density is incredibly small by particle physics standards. The vacuum should have enormous energy according to quantum field theory. Virtual particles constantly appear and disappear. Every quantum field contributes energy to empty space. Add up all these contributions and you get a number about 120 orders of magnitude larger than the observed dark energy density. This is the worst prediction in physics, off by more than one, followed by 120 zeros. Something is wrong. Either quantum field theory is completely wrong about vacuum energy, which seems unlikely given its success in other areas, or something almost perfectly cancels the vacuum energy, leaving only a tiny residue that happens to be the dark energy we observe. But what could cause such perfect cancellation? Why would it be almost but not exactly perfect? Some physicists invoke the multiverse. If countless universes exist with different vacuum energies, we necessarily observe one of the rare universes where vacuum energy is small enough to allow structure formation. Most universes have such large vacuum energy that space expands so fast nothing can ever form. Galaxies, stars, planets, life, all impossible. We observe a life-compatible vacuum energy not because it's natural, but because observers can only exist in universes where it's small. This anthropic explanation is unsatisfying. It answers the question by saying the question is wrong. We observe what we observe because we must. No deeper explanation exists. But acceleration might be telling us something more interesting. What if expansion is not caused by space stretching at all? What if what we interpret as accelerating expansion is actually something else? Some researchers have proposed that the illusion of acceleration could arise if we live in an underdense region of the universe, a large void where matter density is below average. If we're in a void, light from distant supernova would travel through space that's less dense than the cosmic average. This affects how we interpret distances and infer expansion rates. We might conclude expansion is accelerating when really we're just observing effects of local inhomogeneity. Other proposals suggest acceleration might be telling us that general relativity breaks down on cosmological scales. Maybe gravity works differently over billions of light years than it does in the solar system. Modified gravity theories have been constructed that mimic dark energy without requiring any new substance filling space. Gravity could become repulsive at large distances or weak enough that the universe expands faster than Einstein's equations predict. These theories are constrained by observations. Gravitational waves travel at the speed of light, which rules out many modified gravity models, but some survive. Or maybe the problem is more fundamental. Maybe our entire cosmological framework is wrong. Not slightly wrong, deeply wrong. Maybe the universe is not homogeneous on large scales. Maybe the cosmological principle is false. Maybe different regions expand at different rates. Maybe expansion itself is not a global phenomenon, but something that varies across space. Maybe what we interpret as uniform cosmic expansion is actually an average over a much more complex reality. A reality where space does different things in different places for reasons we haven't grasped because we've been forcing observations into a framework that assumes uniformity. The acceleration of cosmic expansion is real. The observations are robust, but what does it mean? Is space really expanding faster and faster, driven by mysterious dark energy filling every cubic centimetre of vacuum? Or is something else happening that looks like acceleration when viewed through our theoretical lenses? We measure redshifts of distant galaxies. We measure their brightnesses. We fit these to models of expanding space. The models work, but do they capture what's actually happening? Or are they convenient approximations of a more complex reality we haven't yet understood? The acceleration nobody expected might be the clue. The hint that expansion is not what we think it is, that the universe is doing something we can describe mathematically but don't yet truly understand physically. Ask a physicist what space is and watch them struggle. Space is the thing between objects, the arena where physics happens, the three-dimensional stage on which matter and energy perform. But what is it made of? What is its substance? Here the answers get vague. Space is not made of anything. It's just geometry, the structure that allows you to define distances and directions. This sounds sophisticated, but it's not really an answer. It's a description of what space does, not what space is. In Newton's universe, space was absolute, an unchanging background, a fixed stage existing independently of anything in it. Objects moved through space, but space itself didn't move or change. This picture is intuitive. Space is like an empty room. Objects can move around inside the room, but the room itself stays the same. Einstein shattered this picture with general relativity. Space is not absolute. It's not independent of matter. Matter curves space. Space tells matter how to move. Space and time are unified into space-time, a four-dimensional structure that's dynamical, changeable, responsive to energy and mass. But even in general relativity, what space is remains murky. The mathematics describes a metric tensor, a mathematical object that encodes distances and angles. But the metric is not the space itself. It's a description of the geometry. The question of what has that geometry remains unanswered. Some physicists treat space-time as fundamental. It's not made of anything more basic. It simply is. The universe is space-time plus fields plus matter. Space-time is the substrate, the bottom layer. You can't ask what it's made of because it's the thing everything else is made in. Other physicists think space-time emerges from something deeper. Quantum gravity theories suggest that, at the Planck scale, around 10 to the minus 35 meters, space-time might dissolve into something else. Loop quantum gravity describes space as woven from discrete quantum threads. String theory imagines space as a structure built from vibrating strings in higher dimensions. These theories are speculative, unproven, possibly wrong, but they take seriously the idea that space-time is not fundamental, that asking what space is made of is not a category error, but a genuine question with an answer we haven't yet found. This matters for expansion, because if we don't know what space is, we can't really know what it means for space to expand. Saying space stretches is a metaphor. What's actually stretching? If space is geometry, what does it mean for geometry to grow? Geometry is relational. It describes the distances and angles between things. Does geometry exist independently of the things it relates? Can you have geometry without objects? Can space exist where there's nothing in it? These seem like philosophical questions, but they have physical implications. Consider the edge of the universe. If space is infinite, there's no edge. But if space is finite, created during the Big Bang and expanding since, there must be an edge, the boundary between where space exists and where it doesn't. What's beyond that boundary? The standard answer is nothing. Not empty space, literally nothing. No space, no time, no possibility of existence. This is hard to think about. Nothing is not a place. You can't point to where nothing is because pointing implies direction, and direction implies space. Beyond the edge of space is not anywhere. It's nowhere. Not somewhere that happens to be empty, nowhere in the fullest sense. But this raises questions. If space is expanding, is it expanding into something? Are we creating new space at the edge? If so, from what? How does something come from nothing? The standard cosmological answer is that these questions are confused. Space is not expanding into anything. The distances between objects in space are increasing, but there's no external arena into which space grows. The universe is all there is. Asking what it expands into is like asking what's north of the North Pole. The question has no meaning. Yet this answer feels incomplete. If distances are increasing, something is changing. What is that something? If it's not space growing into an external void, what is it? Some researchers have proposed that expansion is not space stretching, but particles gaining mass over time. If fundamental particle mass is increased, the universe would look like it was expanding, even if space remained static. Atoms would get larger, light waves would stretch, everything would scale up together in a way that mimics expansion. This sounds bizarre, but it's allowed by general relativity. You can formulate cosmology where masses grow instead of space expanding. The math works. The predictions match observations. It's experimentally indistinguishable from standard expansion. This illustrates a deep point. Expansion might not be a unique interpretation of observations. Different theoretical frameworks can explain the same data. Space expanding, masses growing, perhaps other options we haven't imagined. All mathematically consistent, all matching observations. How do we choose? Usually by simplicity. Space expanding is the simplest description given general relativity, but simplicity is a guide, not proof. The simplest explanation is not necessarily the correct one. Quantum mechanics adds another layer. At quantum scales, space might not be continuous. It might be discrete, composed of fundamental units. If space is quantized, what does it mean for space to expand? Do the fundamental units grow in size? Or do new units appear between existing ones? Or does quantum space work so differently from our intuitions that these questions don't apply? We don't know. Quantum gravity is unsolved. We lack a theory that fully describes space at the Planck scale. Until we have that, our understanding of what space is remains incomplete. And if our understanding of what space is remains incomplete, our understanding of what it means for space to expand must also be incomplete. We describe expansion with great mathematical precision. We measure it accurately, but we don't truly understand it. We're like someone who can perfectly describe how a car moves without understanding engines. The description is accurate, the predictions are precise, but the underlying mechanism remains mysterious. Expansion is like that. We know how it behaves, we can calculate its effects. But what's actually happening? What is doing the expanding? Until we know what space really is, we can't fully answer what cosmic expansion really means. Imagine two galaxies on opposite sides of the observable universe. Each is about 46 billion light years from us in opposite directions. That makes them about 92 billion light years apart from each other. Light has been travelling since the Big Bang for 13.8 billion years. So light from one galaxy has had 13.8 billion years to reach us. And light from the other galaxy has also had 13.8 billion years to reach us. But light from one galaxy has not had time to reach the other galaxy. They're too far apart. Even travelling at the speed of light since the beginning of the universe, a signal from one couldn't have reached the other. They've never been in causal contact. No information has ever passed between them. They exist in causally disconnected regions of space. Yet when we measure the cosmic microwave background from opposite sides of the sky, from these causally disconnected regions, it has the same temperature to 1 part in 100,000. How is this possible? How can two regions that have never communicated have exactly the same properties? It's like finding two people on opposite sides of the world speaking the exact same language, wearing identical clothes, with the same customs and beliefs, despite never having met or descended from common ancestors. How did they coordinate? This is the horizon problem. It's one of the fundamental puzzles of cosmology. Cosmic inflation solves it elegantly. If the universe underwent a brief period of exponential expansion in its first moments, Regions that are now far apart were once close together, close enough to exchange information and reach thermal equilibrium. Then inflation stretched space so rapidly that these regions were blown apart to vast distances. They look causally disconnected now, but they were connected in the past, before inflation separated them. This explains the uniformity of the cosmic microwave background. All regions were in contact during the pre-inflation era. They had time to equilibrate to the same temperature. Then inflation froze that uniformity and blew space up to cosmic scales. Beautiful, elegant, almost universally accepted. But here's what's strange about this solution. It requires space to have expanded faster than light, much faster. During inflation, space expanded by a factor of at least 10 to the 26th in about 10 to the minus 30 seconds. That's space growing by more than 1,000,000,000,000,000,000,000 trillion times in a tiny fraction of a second. The expansion velocity was far, far greater than the speed of light. How is this not a violation of relativity? The standard answer is that special relativity forbids objects moving through space faster than light, but it says nothing about space itself expanding. Space can expand at any rate. There's no speed limit on expansion. This is technically correct. The mathematics of general relativity allows it, but it's conceptually troubling. If space can expand arbitrarily fast, what does that mean? How is it different from faster than light motion? If two galaxies move apart faster than light due to expansion, why can't they communicate? The light traveling between them should eventually reach, if given enough time, but it doesn't if expansion is too fast. Here's the issue. Light travels through space at speed c. If space expands faster than c, light makes no progress. It's like running up a down escalator that's moving faster than you can run. You're moving, but you never get anywhere, because the escalator is pulling you back faster than you're advancing. Light between separating galaxies works the same way. It's moving through space at c, but space is expanding so fast that the distance to the destination increases faster than light can cross it. Light never arrives. Communication is impossible. The regions are causally disconnected, despite light trying to bridge the gap. But this means expansion has physical effects. It prevents communication. It isolates regions. If it has physical effects, how is it different from motion? If two observers are separating faster than light due to expansion, their situation seems indistinguishable from both being stationary while space expands or both moving through space faster than light. The mathematics treats these scenarios differently. The predictions are different. But physically, observationally, what's the difference? Maybe there is no difference. Maybe expansion being space stretching versus objects moving is just a choice of coordinates. General relativity is coordinate independent. You can describe physics in many different coordinate systems. Expanding space is one choice. Objects moving through static space is another. Both can describe the same physical situation if you choose coordinates appropriately. Maybe asking whether space really expands or objects really move is asking the wrong question. Maybe these are just two ways of describing the same reality, neither more fundamental than the other. But if that's true, it suggests something profound. It suggests expansion is not a thing that happens to space. It's a description we use for certain physical situations, a convenient way of organizing observations. The universe is doing something. We can describe it as expansion. We can describe it other ways too. The descriptions make different things easy or hard to calculate, but none is the true description of what's really happening. They're all models, approximations, useful fictions that let us predict and understand. This might seem like giving up. If expansion is not really real, if it's just a description, what are we doing in cosmology? But it's not giving up. It's recognizing the limits of our knowledge. We know the universe is doing something that causes distant galaxies to redshift. We can model this as expansion. The model works incredibly well, but the model is not reality. It's a map. And the map is not the territory. The territory is whatever the universe is actually doing. The map helps us navigate. it makes predictions, it guides research. But we shouldn't mistake the map for the territory. The horizon problem is solved by inflation, but inflation requires space expanding faster than light. Faster than light expansion requires thinking of space as a substance that can stretch. But space as substance that stretches is philosophically problematic and mathematically non-unique. Other coordinate choices describe the same physics without space stretching. So what's actually happening? The honest answer is we don't know. We have excellent mathematical descriptions. The Friedman equations work. Inflation solves the horizon problem. Dark energy explains acceleration. All true, all useful. But the question of what's really happening, what the universe is actually doing that we're describing with these models, remains unanswered. Maybe unanswerable. Maybe physics is just about predicting observations and expansion is a successful prediction scheme. Or maybe deeper understanding is possible and we haven't reached it yet. The horizon problem is solved by a model, but whether the model captures what's really happening is still a mystery. Let's talk numbers. The Hubble constant measures cosmic expansion rate. How fast is the universe expanding right now? Give me a number in kilometers per second per megaparsec. Simple question. Should have a simple answer, except it doesn't. Different measurements give different answers, and the answers disagree badly enough that cosmology is in crisis. Not because we can't measure expansion, we measure it very precisely. The problem is we get different, precise values depending on how we measure. The precision makes the disagreement worse, not better. Two methods dominate. First, the early universe approach. Measure the cosmic microwave background with exquisite precision using satellites like Planck. Fit the data to cosmological models. Extract the Hubble constant as one of the parameters. This gives about 67.4 kilometers per second per megaparsec. Precision is better than 1%. Very confident result. Second, the late universe approach. Measure distances to galaxies using standard candles like Cepheid, variable stars, and Type 1a supernovae. Compare distances to redshifts. Calculate expansion rate directly. This gives about 73 kilometers per second per megaparsec. Also precision, better than 1%. Very confident result. The problem is these two confident results disagree by about 9%. That's not huge in absolute terms, but it's 6 sigma statistically. The probability that this is random chance is less than 1 in a million. Something is wrong. Either one measurement is systematically biased in ways we haven't identified, despite exhaustive checking, or both measurements are correct and something about our cosmological model is fundamentally wrong. A missing ingredient, a misunderstanding. Something that causes the early universe to predict one expansion rate, while the late universe actually expands at a different rate. This is called the Hubble tension, and it's dominated cosmology conferences for the past decade. Hundreds of papers propose solutions. Maybe dark energy evolves. Maybe there's early dark energy that affects the cosmic microwave background differently than late-time observations. Maybe neutrinos are more massive than we think. Maybe there's a new light particle we haven't detected. Maybe gravity works differently on large scales. Maybe. None of the proposals is clearly right. Most create new problems while solving the Hubble tension. The tension persists. More data makes it worse instead of better because the measurements become more precise while continuing to disagree. But here's what's really strange. The Hubble tension might be telling us that expansion is not what we think it is. Consider what the tension means. The early universe, as measured by the cosmic microwave background, predicts one expansion rate. The actual measured expansion rate today is different. This is not just saying we got the measurement wrong. This is saying the universe's expansion evolved differently than our models predict. The model says, if the early universe looked like this, the late universe should expand like that. But it doesn't. it expands differently. This could mean dark energy is not constant. That's the conventional interpretation. Dark energy has energy density. If that density changed over time, expansion rates would evolve differently than a cosmological constant predicts. But dark energy has been measured to be extraordinarily constant. Multiple independent observations show its density doesn't change measurably across billions of years. How can it be constant yet cause the Hubble tension? Something doesn't add up. Or maybe the tension is telling us that space doesn't expand uniformly. The cosmological principle assumes the universe looks the same everywhere on large scales. Expansion rate should be the same in all directions. But what if it's not? What if we live in a region where expansion is faster than the cosmic average? Local measurements would give higher values than early universe predictions based on global properties. The Hubble tension would be explained by inhomogeneity. We're in an unusual spot, not typical. Our local measurements don't represent the cosmos as a whole. This sounds far-fetched, but it's testable. If expansion varies across space, we should be able to detect it. Measure expansion in different directions. If it's truly uniform, every direction gives the same answer. If we're in an underdense region, expansion might be directionally dependent. Some studies claim to find hints of this. Others find no evidence. The data quality is not yet good enough to settle the question definitively, but future surveys will have the precision. Within a decade, we'll know if expansion is truly isotropic or varies across the sky. The most radical interpretation is that expansion is not fundamental. What if the universe is not actually expanding in the sense of space stretching? What if what we measure as expansion is a consequence of something else? Some deeper phenomenon that manifests as apparent expansion when observed, but is actually something different. This sounds crazy, but consider the options. Either one of our most precise measurements is wrong, despite being checked exhaustively, or our model of the universe is missing something major, or expansion itself is not what we think. None of these is comfortable, but one of them must be true. The Hubble tension is not going away. Better data from the James Webb Space Telescope will refine distance measurements. Better cosmic microwave background observations will tighten early universe predictions. The two approaches will clash with even greater precision, unless something changes, unless we find the missing ingredient that reconciles them, unless we realize that our framework for understanding expansion needs revision. The crisis is forcing us to question assumptions, to look beyond standard models, to consider possibilities that seemed too radical just years ago. And that's healthy. That's how science progresses. The Hubble tension is not a failure. It's an opportunity, a crack in the foundation that might lead to deeper understanding. The universe is trying to tell us something through this disagreement. We just have to figure out what. Every introductory astronomy course teaches the same story. Light from distant galaxies is redshifted. Wavelengths are stretched. Colors shift toward the red end of the spectrum. Why? Because space is expanding. As light travels through expanding space, the expansion stretches the light waves themselves. Longer wavelengths mean redder light, simple, intuitive. The cosmic redshift is direct evidence that space expands. This explanation is in every textbook, every popular science book. It's how we know the universe is expanding, except this explanation is incomplete at best and possibly wrong at worst. Here's the problem. Redshift is real. We measure it precisely. Galaxies billions of light years away show redshifts of 6, 7, 8 or more. Their light has been stretched to wavelengths many times longer than when emitted. This is observational fact, but why does this happen? The textbook answer is space expanding stretches light, but there's another explanation that works equally well mathematically. The Doppler effect. Galaxies are moving away from us through space. Moving sources produce Doppler-shifted light. Recession creates redshift. No need for space to expand at all. just motion through static space. You might object that these are different. Space expanding versus objects moving should be distinguishable. At low speeds, they're similar, but at cosmic distances, they diverge. Expansion redshift and Doppler redshift have different formulas, different predictions, except they don't. Not really. General relativity allows multiple coordinate descriptions of the same physical situation. You can describe cosmology using expanding space coordinates, or you can use static space coordinates where galaxies move. Both are valid. Both make the same predictions for observable quantities. Redshift is one of those observables. The redshift formula depends on your coordinate choice, but the actual measured redshift is the same regardless of how you choose to describe what's happening. This is deeply unsettling. It means asking whether redshift is really due to expansion or really due to motion is asking a meaningless question. General relativity doesn't distinguish. The mathematics treats them as different coordinate descriptions of identical physics. Observers can't tell the difference by measuring redshift alone. You need additional information, additional measurements. But even then, you're not determining which description is true. You're determining which description is more convenient for organizing observations. Some physicists argue that the expanding space description is preferred because it's simpler. It makes the universe homogeneous and isotropic. Galaxies at rest with respect to the cosmic rest frame. Expansion carries them apart without motion. This respects the cosmological principle nicely, but simplicity is aesthetic preference, not physical requirement. Nature doesn't care about our aesthetic preferences. If motion through static space describes observations equally well, nature is not obligated to choose the simpler description. Other physicists point out that expansion and motion have different energy implications. Objects moving through space have kinetic energy. Galaxies being carried by expansion don't. This seems like a real physical difference, but it's not so clear. Energy in general relativity is tricky. There's no unique definition of total energy in a curved space-time. The energy you calculate depends on your choice of coordinates. In expanding coordinates, galaxies have no kinetic energy. In static coordinates, they do, but the total energy of the system can be the same in both descriptions. Energy differences depend on reference frames. They're not absolute. The real issue is that redshift alone doesn't tell you what's happening. It tells you that wavelengths change between emission and observation. Why they change requires interpretation. Interpretation means choosing a theoretical framework. The framework determines what you conclude about reality. Change the framework and you change the conclusion. This doesn't mean anything goes. Frameworks must match all observations, not just redshift, but multiple frameworks can match observations. And we can't use observations alone to determine which framework is really correct, because observations are interpreted through frameworks. This is frustrating. We want physics to tell us what's really happening, not give us multiple descriptions that all work. But maybe that's the lesson. Maybe physics is fundamentally about predictions, not ontology. Maybe asking what's really happening is asking physics to do something it can't do. Maybe we should be satisfied with having multiple valid descriptions and use whichever is most convenient for the problem at hand. This is the instrumentalist view. Physics is a tool for prediction, not a window into ultimate reality. But most physicists are not instrumentalists at heart. We want to understand reality, not just predict observations. The fact that general relativity allows multiple descriptions of redshift suggests our current framework is not complete. A more complete theory might distinguish between expansion and motion in ways general relativity doesn't. Quantum gravity might provide that distinction, or a deeper understanding of what space is might make clear which description is fundamental and which is emergent. Until then, we're stuck with ambiguity. Redshift is the primary evidence for cosmic expansion, but redshift is compatible with multiple interpretations. We choose expanding space because it fits neatly with the Big Bang model and the cosmological principle. But this is choice, not necessity. The universe could be doing something else that produces the same redshifts. We wouldn't know from redshift measurements alone. This doesn't mean expansion is wrong. It means expansion is one interpretation among possibilities, an interpretation that works. That makes good predictions, but not the only possible interpretation, and maybe not the deepest description of what's actually happening. The universe is redshifted, that's fact. Expansion is interpretation, and interpretation, however useful, is not the same as truth. This matters because if we don't understand what redshift really means, we can't be sure we understand what the universe is really doing. And if we don't understand that, all our cosmology might be built on assumptions that are convenient but not fundamental. The mystery isn't that the universe is expanding. The mystery is whether expansion is what's really happening or just our best current description of a phenomenon we haven't fully grasped. For decades, one idea has refused to die despite being dismissed by mainstream cosmology. Tired light, the proposal that redshift is not due to expansion at all, but to light losing energy as it travels through space, photons getting tired on their long journey across the cosmos. This would produce redshift without any expansion, without any motion, just light gradually shifting to longer wavelengths as it propagates. The idea dates back to the 1930s. It was proposed as an alternative to the expanding universe shortly after Hubble's discovery, and it has been repeatedly rejected by evidence. Yet it keeps coming back. The standard criticisms are powerful. Tired light predicts that distant galaxies should look blurred because light from different parts of the galaxy would have traveled different distances and lost different amounts of energy. This blurring is not observed. Distant galaxies look sharp. Tired light also predicts that the time evolution of supernovae should not depend on distance, but observed supernovae at high redshift evolve more slowly than nearby ones. Time dilation. This is naturally explained by expansion. Time runs slower in the past. In an expanding universe, distant supernovae are in our past. Their light has been travelling for billions of years. We see them in slow motion. Tired light cannot explain this. These arguments convinced most cosmologists decades ago that tired light is wrong. But some researchers never gave up. They pointed out that the criticisms apply to simple tired light models, where photons lose energy through interactions with matter or fields. But there are more sophisticated versions. What if light loses energy in a way that depends on the geometry of space, not through scattering or absorption, but through some intrinsic property of how photons propagate over cosmic distances? This is not the same as simple tired light. It's a modification to how light itself works on cosmological scales. This sounds ad hoc, and it is. You're modifying fundamental physics specifically to avoid expansion. But ad hoc doesn't mean wrong. Lots of correct physics seemed ad hoc when first proposed. Dark matter was ad hoc. Dark energy was ad hoc. We accepted them because evidence forced us. The question is whether tired light, or something like it, could explain observations better than expansion. So far, the answer is no. Expansion explains too much. The cosmic microwave background, the abundance of light elements, structure formation. Tired light struggles with all of these. It was designed to explain redshift, but fails at explaining the broader cosmological picture. Yet there's something intriguing about the idea. What if light does lose energy over cosmic distances? Not enough to replace expansion, but enough to matter. What if there's a small tired light component in addition to expansion redshift? This could explain anomalies, the Hubble tension, for instance. If light from distant galaxies loses a tiny bit of extra energy, we would overestimate their distances. This would make the expansion rate appear faster than it is. Local measurements would give higher Hubble constant values than early universe predictions. Exactly what we observe. This hybrid model, expansion plus a small tired light effect, is testable. Different redshift mechanisms have different signatures. Expansion creates time dilation, tired light doesn't. If the Hubble tension were due to tired light, we should see reduced time dilation in high redshift supernovae compared to pure expansion predictions. Some researchers claim they see hints of this, others don't. The data is not yet precise enough to settle it, but the possibility is there. Why would light lose energy travelling through space? One speculative answer involves the quantum vacuum. Empty space is not really empty. Virtual particles constantly fluctuate into and out of existence. Photons interact with these vacuum fluctuations. Usually we ignore these interactions because they're tiny. But over billions of light years, tiny effects add up. Maybe photons lose a minuscule amount of energy to vacuum interactions over cosmic distances. Not enough to notice in laboratory or even solar system experiments, but measurable over gigaparsecs. This is speculation. There's no confirmed mechanism for such energy loss. No direct evidence it happens, but it's allowed by physics. Nothing forbids photons from having weak interactions with the quantum vacuum that manifest only at cosmological distances. If such interactions exist, they would appear as a tired light component. We would need to include them in our cosmological models. We haven't because we assume they're negligible. But assumptions should be tested. The broader point is that tired light, however implausible, reminds us that redshift interpretation is not unique. We interpret redshift as expansion, but other mechanisms could contribute. Combinations of effects might be at play. We won't know unless we look, and looking means taking seriously ideas that seem wrong, testing them rigorously, ruling them out with evidence rather than assumption. Science progresses by eliminating possibilities. Tired light has been mostly eliminated, but mostly is not completely. Some corner cases remain. Some hybrid models survive. They're unlikely, but unlikely is not impossible. The tired light debate teaches a meta lesson. Cosmology is built on assumptions. Light redshifts because space expands. Space is homogeneous. The cosmological principle holds. These are working assumptions. They've been spectacularly successful, but success doesn't guarantee truth. It guarantees usefulness. Tired light failed because it was less useful than expansion. But failure to be the best model doesn't mean it contributes nothing. Perhaps there's a small tired light effect hidden in the noise. Perhaps expansion is 99% of the story, and tired light is 1%. We wouldn't know because we stopped looking after deciding expansion was right. The universe might be more complicated than our best models capture. Redshift might have multiple causes. Expansion might dominate, but not monopolize. This is worth keeping in mind. Not because tired light is likely correct, it's not, but because the mindset of considering alternatives, of questioning assumptions, of being open to complications is essential for science. The moment we decide we've figured everything out is the moment we stop making progress. Tired light keeps us honest. It reminds us that what we call expansion is really interpretation of observations. An interpretation that works, that's proven itself, but interpretation nonetheless. And interpretations can be refined, modified, sometimes even replaced when better understanding emerges. The cosmological principle is the foundation of modern cosmology. It states that the universe is homogeneous and isotropic on large scales. Homogeneous means it looks the same at every location. Isotropic means it looks the same in every direction. These are profound statements about cosmic structure. They say that nowhere is special, no direction is preferred. The universe is uniform, average over volumes of a few 100 million light years, and everywhere looks statistically identical. This principle simplifies cosmology enormously. If the universe is uniform, we can model it with simple mathematics. The Friedmann equations describing cosmic expansion assume homogeneity and isotropy. The entire framework of standard cosmology rests on this assumption. But what if the assumption is wrong? What if the universe is not actually homogeneous and isotropic on large scales? What if there's structure, variation, and isotropy that we've been ignoring by forcing observations into a uniform framework? This is not wild speculation. This is a serious possibility being investigated by serious researchers because observations are showing cracks in the cosmological principle. Anomalies that are hard to explain if the universe is truly uniform. Start with the largest structures. The Hercules Corona Borealis Great Wall is a structure spanning 10 billion light-years. The universe is only 13.8 billion years old. How did such an enormous structure form? Structure grows through gravitational collapse. Gravity pulls matter together, but gravity is limited by the speed of light. Over cosmic history, there's only been enough time for gravity to organize matter across a certain maximum scale. That scale is smaller than 10 billion light-years. Structures larger than that should not exist, yet they do. Multiple examples have been found. These structures are too large to have formed if the universe is homogeneous, unless they're statistical flukes, rare fluctuations that happen to be large. When you observe enough of the universe, unlikely things occasionally occur. This is the standard explanation. But the probability of multiple such flukes is very low, and we keep finding more. The more we observe, the more giant structures appear. This suggests they're not flukes, but rather common features we didn't expect because our homogeneous models didn't predict them. Then there's the cosmic microwave background anomalies, the axis of evil, the hemispherical asymmetry, the cold spot, all violations of isotropy, all suggesting the universe has preferred directions or regions with unusual properties. Each anomaly individually could be chance. Together, they paint a picture of a universe that's not perfectly uniform, not dramatically inhomogeneous, but subtly structured in ways that violate the cosmological principle. The Hubble tension might also reflect inhomogeneity. If we live in an underdense region, a large void where matter density is below average, expansion would proceed differently here than in typical regions. Our local measurements would not represent the cosmic average. The early universe, measured globally through the cosmic microwave background, would predict one expansion rate. Our local measurements would give another. The tension would be explained by our location being atypical, not special in an anthropocentric sense, just located in a region that happens to be less dense than average. Testing this requires mapping matter distribution across enormous volumes, determining whether we're in a void large enough to explain the Hubble tension. Some studies suggest we might be, others find no evidence for a significant local underdensity. The question remains open, but the fact that it's being asked seriously shows how far we've come from blind faith in the cosmological principle. If the universe is inhomogeneous, our entire cosmological framework needs revision. The Friedmann equations assume homogeneity. They don't apply to an inhomogeneous universe. You need more complicated equations. Einstein's field equations in full generality. No symmetry assumptions. No simplifications. These equations are fiendishly difficult to solve. Even numerically, simulating an inhomogeneous universe is far harder than a homogeneous one. Cosmologists have avoided this complexity by assuming uniformity. But if observations force us to abandon that assumption, we're in for a lot of hard work. An inhomogeneous universe also changes what expansion means. In a homogeneous universe, expansion is global. Space expands uniformly everywhere. In an inhomogeneous universe, expansion can vary. Different regions expand at different rates. Space itself becomes more complex. Not a simple expanding background, but a dynamic structure with variations. This is closer to what general relativity allows in full generality. Homogeneous cosmology is a special case. Real universes might be messier. Some researchers have argued that inhomogeneity could replace dark energy. In homogeneous models, you need dark energy to explain acceleration. But in inhomogeneous models, the nonlinear effects of structure might mimic acceleration. Overdense regions collapse and underdense regions expand faster. Average these effects and you might get apparent acceleration without any dark energy component. This is controversial. Most analyses suggest the effect is too small, but the possibility exists. Maybe dark energy is an artifact of assuming homogeneity when reality is inhomogeneous. The cosmological principle has served us well. It allowed the development of Big Bang cosmology. It made predictions that have been confirmed, but it might be an approximation, useful but not exact, good enough for rough calculations, but breaking down when precision increases. We're entering an era of precision cosmology. Measurements are good enough to test the cosmological principle directly rather than assuming it. And the tests are showing tensions. Nothing definitive yet, nothing that proves inhomogeneity, but enough to make the question serious. If the universe is not uniform, that changes everything. Our distance measurements might be biased. Our expansion rate calculations might be averages over varied regions rather than global constants. Dark energy might be unnecessary. The entire structure of cosmology would need rebuilding on a more complex foundation. This is scary. Decades of work potentially needing revision. But it's also exciting, a chance to move beyond approximations to more accurate descriptions of reality. A challenge that will keep cosmologists busy for generations. The cosmological principle is under siege, not defeated, not abandoned, but questioned as never before. And that questioning might lead to the next revolution in our understanding of the cosmos. Here's a thought experiment. Imagine two universes. In universe A, space expands uniformly at a rate described by the Hubble constant. Galaxies remain at rest with respect to the cosmic rest frame. Expansion carries them apart without motion. Redshift is caused by light waves being stretched as they travel through expanding space. In universe B, space is static. It doesn't expand. Galaxies move through this static space at velocities proportional to their distances. Redshift is caused by Doppler effect from motion. These seem like completely different universes, different physics, different mechanisms. They should be distinguishable, except they're not. They're the same universe described in different coordinates. This is not semantic trickery. This is how general relativity works. The theory is coordinate independent. Physical predictions don't depend on your choice of coordinates. You can describe the same physical situation using different coordinate systems. The coordinates are human bookkeeping, not physical reality. In one coordinate system, space expands and galaxies are stationary. In another, space is static and galaxies move. Both are valid, both make identical predictions for measurable quantities. Redshift, distance, luminosity, everything observable is the same in both descriptions. You cannot use observations to determine which description is really correct because the question has no meaning. They're both correct. They're both descriptions of the same reality using different mathematical language. This is profoundly disturbing if you think physics should tell you what's really happening. If expansion versus motion is just a coordinate choice, what is the universe actually doing? The answer general relativity gives is that this is the wrong question. The universe is described by a metric tensor, a mathematical object encoding geometry. Different coordinates give different expressions for the metric, but the metric itself, the geometric reality, is coordinate independent. What's really happening is described by the metric, not by any particular coordinate choice. But this is unsatisfying. The metric is mathematics, abstract structure. We want to know what's physically happening. Is space a thing that can stretch? Or is space static and objects move through it? These seem like physical questions about reality, not just coordinate choices, yet general relativity treats them as equivalent. Both are valid ways to foliate spacetime, to slice the four-dimensional structure into three-dimensional spaces evolving over time. The foliation is human choice, not nature's. Some physicists embrace this. They say cosmology is about predicting observations, not determining ultimate reality. Whether you describe the universe as expanding space or moving galaxies is a pragmatic choice. Use whichever is more convenient. For most purposes, expanding space is simpler. It respects the cosmological principle naturally, makes equations easier, but for some calculations, static space might be more convenient. Use that instead. Neither is more true, both are tools. Other physicists find this intolerable. Physics should discover truth about nature, not just make predictions. If expansion is real, it should be distinguishable from motion. If it's not distinguishable, maybe that tells us something profound. Maybe what we call expansion is not fundamental. Maybe it's an emergent description, something that appears in certain coordinate choices but isn't a basic feature of reality. Like temperature. Temperature is real and measurable, but it's not fundamental. It emerges from the statistical behavior of particles. Individual particles don't have temperature. Collections do. Maybe expansion is like that, a statistical or emergent property that appears at large scales but isn't part of the microscopic description. This connects to quantum gravity. General relativity describes space-time classically, but at the Planck scale, quantum effects dominate. Space and time might be emergent structures arising from something more fundamental. String theory suggests space-time emerges from strings and brains. Loop quantum gravity suggests it emerges from discrete quantum geometry. In both cases, classical space-time, with its expansion and curvature, is not fundamental. It's an approximation valid at large scales. The real physics happens at the Planck scale, where space-time dissolves into something else. If space-time is emergent, expansion is definitely not fundamental. It's a feature of the emergent description. Asking whether space really expands is like asking whether temperature really exists. It exists as an emergent phenomenon. But it's not fundamental. The fundamental description is in terms of quantum degrees of freedom that don't directly map onto expanding space. We use expanding space because it works, because it's the right description at scales we observe, but it's not the deepest description. This suggests that the question of what expansion really is might not have an answer within general relativity. General relativity is a classical theory. It describes space-time geometry classically. Within that framework, expansion is coordinate dependent, not a unique physical fact. To get beyond this, we need quantum gravity, a theory that describes space-time more fundamentally. That might tell us whether expansion is fundamental or emergent, whether it's a real feature of nature or a convenient description we use because we don't have access to the deeper quantum structure. We don't have quantum gravity yet. String theory and loop quantum gravity are candidates, but neither is confirmed. Until we have a working quantum theory of space-time, questions about what expansion really is remain open. We can describe expansion mathematically, predict its effects, measure it precisely, but understand it deeply. That requires knowing what space is at a fundamental level, and we don't know that yet. This is humbling. Cosmology is incredibly successful. We've measured cosmic expansion to percent-level precision, traced it back to the Big Bang, predicted the cosmic microwave background, explained structure formation, all triumphs of the expanding universe framework. But at the deepest level, we don't understand what we're describing. We know how expansion behaves, not what it is. We have a model that works, not a theory of reality. This distinction matters because it reminds us how much we still don't know, how far we are from complete understanding. Expansion is not the mystery. Understanding expansion is. Strip away the theory, ignore the models. What do we actually observe? Not expansion. We never observe expansion directly. We observe redshift. Galaxies emit light at specific wavelengths. That light reaches us with longer wavelengths. The shift is measured precisely. This is raw observation. Everything else is interpretation. We interpret the redshift as evidence of expansion. But interpretation requires theory. Theory involves assumptions, and assumptions can be questioned. Here's what we know for certain. Redshift correlates with distance. The farther away a galaxy is, the more its light is redshifted. This correlation is extremely tight. It's linear for nearby galaxies. For distant galaxies, it deviates from linearity in predictable ways. We can measure redshift spectroscopically. We can estimate distance using standard candles like supernovae, plot redshift versus distance. And you get a relationship. This relationship is real. It's observational fact, independent of any cosmological model. What causes this relationship? The expanding universe model explains it beautifully. Space expands. Light waves get stretched. More distant galaxies have light that's travelled longer through expanding space. More stretching, more redshift. The model predicts the exact relationship we observe, including the deviations from linearity for distant galaxies. This is why the expanding universe model succeeded. It explained observations that had no other explanation at the time. But now we know general relativity allows multiple interpretations. The relationship between redshift and distance could be described as motion through static space, or as a combination of expansion and motion, or as something else entirely if we allow modifications to general relativity. Each interpretation makes predictions. Most make the same predictions for redshift versus distance. They differ in other predictions, like time dilation or the cosmic microwave background. These additional predictions are what distinguish models, not redshift alone. The cosmic microwave background is another raw observation. We measure radiation coming from all directions in the sky. The radiation is thermal, with a temperature of about 2.7 Kelvin. It has tiny fluctuations, hot spots and cold spots at the level of 1 part in 100,000. These fluctuations have specific statistical properties. Again, this is observation. Interpretation is separate. We interpret the radiation as photons from the early universe, from when the cosmos was 380,000 years old, when space was filled with hot plasma that cooled enough for electrons and protons to combine into neutral atoms. The photons we see today are from that era, redshifted by expansion to microwave wavelengths. This interpretation is extremely successful. It explains the temperature, the blackbody spectrum, the fluctuations. Everything about the cosmic microwave background makes sense in the Big Bang plus expansion framework. But again, this is interpretation. The raw data is photons hitting our detectors. The story we tell about where they came from and why they look the way they do is model dependent. Distance measurements are also more complex than they seem. We use standard candles, objects with known intrinsic brightness, measure how bright they appear, calculate distance from the inverse square law. Sounds straightforward, but intrinsic brightness must be assumed or calibrated. For Cepheid variables, we use a period luminosity relation. For supernovae, we assume all type 1 supernovae have similar peak brightness. These assumptions are justified empirically. They work, but they're still assumptions. If something systematically affected the brightness of distant supernovae, we would misestimate distances, and we'd never know from observations alone because we need the distance to check the brightness. This creates a circularity. We use standard candles to measure distances. We use distances to determine expansion. we use expansion to interpret redshift. Each step involves assumptions that are justified by the consistency of the whole framework. But consistency doesn't guarantee correctness. Multiple frameworks could be internally consistent while describing reality differently. We choose the expanding universe framework because it's simple and works, not because we've proven it's uniquely correct. Even the concept of distance at cosmic scales is slippery. We defined multiple distance measures earlier. Each gives different values. When we say a galaxy is 10 billion light years away, which distance do we mean? Usually we mean light travel distance, the distance light traveled to reach us. But in an expanding universe, this is not the galaxy's current proper distance. That's larger because space expanded while light was traveling. So the galaxy is now farther away than 10 billion light years, even though its light took 10 billion years to reach us. But now is ambiguous in relativity. Simultaneity is observer-dependent. There's no absolute sense in which the galaxy is at a specific distance now. Distance at cosmic scales is not a simple concept. It's model-dependent and definition-dependent. This is not saying observations are unreliable. They're very reliable. We measure redshifts, brightnesses, temperatures, all with great precision. But what we infer from those measurements depends on theoretical frameworks. The frameworks work. They make predictions that match observations, but they're not the only possible frameworks. And when observations start showing tensions, like the Hubble tension, it suggests maybe our framework is incomplete. Maybe there are aspects of reality it doesn't capture. Maybe we're measuring real things, but interpreting them through a lens that's approximately, but not exactly correct. What are we really measuring when we measure expansion? We're measuring the redshift at distance relationship. We're measuring the cosmic microwave background. We're measuring how fast galaxies recede. All of these are genuine measurements, real data. But expansion itself? That's interpretation. The universe is doing something that produces these measurements. We call that something expansion. The name is useful. The concept works. It organizes observations and makes predictions. But whether space is literally stretching, or whether some other physics produces the same observational signatures, is not settled. Maybe not even settable within general relativity. Maybe only answerable with quantum gravity. Or maybe the question is fundamentally ambiguous. Maybe asking what's really happening is the wrong question. Maybe reality just is what we measure, and all interpretations that match measurements are equally valid ways of describing it. This is where physics gets philosophical, where we confront limits of what science can tell us. We can measure, we can predict, we can build models that organize measurements. But can we know what's really real? What's actually happening as opposed to what we describe as happening? Maybe, maybe not. The universe is expanding. That's our best current description. But that's not the mystery. The mystery is whether description equals understanding, whether matching observations means comprehending reality, whether the map is the territory or just a useful guide through territory that remains fundamentally mysterious. We've measured expansion for a century. We've built an entire cosmological framework around it. But do we understand it? That question remains open. And maybe that's okay. Maybe that's what keeps us searching. The universe is expanding. This much we know. Observations confirm it beyond reasonable doubt. But expansion, as we describe it, space stretching, carrying galaxies along, wavelengths stretching with it, this might be interpretation rather than reality. A framework that works, that predicts, that organizes observations beautifully, but perhaps not the deepest truth about what's actually happening at the foundation of cosmic evolution. The mystery is not the phenomenon. The mystery is understanding what the phenomenon really is.